And now I'd like to introduce today's speakers. Dave O'Connor has worked in the air pollution control industry since 1982. The majority of his time has been spent on the applications portion of the business. Since 1982, Dave has been directly involved in the design and production of the 304 Fiberbed filter systems in numerous industries. Rich Stone is a mechanical engineer who brought the wealth of experience gained in his prior work experience, which includes a nuclear power and refinery background business, to the APC business. Responsible for the design, manufacturing, and service of equipment manufactured by AirClear LLC, Rich has a unique perspective related to the proper design of FBME. A provider of air pollution control equipment, AirClear LLC designs custom solutions for a varied customer base rooted in the manufacturing and refining markets. AirClear designs and manufactures 3 core products at its Elkton, Maryland facility. Its primary products include thermal oxidizers, regenerative and recuperative, as well as FBME, aka Mist Eliminators, Coalescing Fiberbed filters. AirClear augments its primary products with scrubbers and shell and tube heat exchangers. And now to get this webinar officially started, here are Rich and Dave, starting off in the form of a question that they hope to answer today. Rich and Dave, go right ahead.
Even when you get what you pay for, did you get the most value for your money?
Yes, that may be a better way to phrase the question. But regardless of how you state it, understanding the key design criteria for the design of a fiberbed mist eliminator is an essential step to a successful project. Rich, some of our participants may not fully understand exactly how a fiberbed mist eliminator works. Can you explain the primary mechanics involved in the filtration process?
The fiberbed filters work by interception, impaction, and Brownian motion. Each removes particles in different size ranges and allows the liquid aerosol to be coalesced into larger droplets where gravity can move them down into the bottom of the sump. The filter elements themselves are referred to in many different ways.
Yes, the name candles came about because of their long cylindrical shape, similar to a candle. Fiberbeds, coalescing filter, fiberbed mist collectors, or just plain filters. All of these names are used interchangeably.
The number of filters is determined by the airflow, cubic feet per minute, and the design velocity range selected.
To best understand this time-proven technology, I think a brief look at its origin would be worthwhile.
The mist eliminators were developed at the Hanford Project in Washington in the late 1940s. They were doing some work for the government where they had some aerosol mists that they definitely did not want to get into the atmosphere. So they developed the research project to come up with the best filters to remove aerosol mists.
The final design report, which was developed by General Electric, who was the contractor for the Atomic Energy Commission, is extensive and full of great technical data collected during the research and development phase.
I find the way the team worked together to find a solution to a very difficult process is very impressive. The detail that they went into in this test was very impressive. For example, they changed the conditions of the superficial air velocity, the bed depth, the packing density, the types of glass, types of fibers, and a study of the expected service life of the glass fiber filters.
Literally, we are just hitting on a few of the key points in very general terms in this discussion. The background is important because the design criteria investigated and developed by General Electric and the AEC at that time are still in use today.
The bottom line from this study, as we can see in this statement, is the team was very pleased with their findings to develop a filter that removes such a high percentage of the aerosol mist.
As so often happens with technology, over the years it is adapted and applied to other areas. And as technology evolves, it moves into different industries and becomes an industry in its own right. And that's really what happened with fiberbed mist eliminators.
Numerous processes have been cost-effectively filtered, preventing incalculable tons of emissions from entering the atmosphere. Okay, we know now how well the fiberbed mist eliminators work and for how long they have been doing this job. There are really three primary objectives that are critical in designing an air pollution control system.
Well, first, an engineer has to be certain that the performance will meet the air emission regulations that they are required to meet. And next, he also has to minimize the cost. Throwing money at a problem seldom is a good solution. And finally, the engineer must want a system that has minimal impact on the bottom line, low operating cost and maintenance cost.
Yes, and that's how we all keep our jobs. Let's look at the most important aspects for the design of a fiber mist eliminator.
Design of the fibers themselves relates to the system's overall efficiency and durability. The fiber diameter and the material used to make the fibers are key elements in the design.
True, but the selection of fiber diameter and material are generally outside of the plant engineer's control. They are under the system provider's fundamental design.
Yes, but asking the right questions about the fibers can help avoid a costly mistake.
The Hanford report does a great job of explaining how important the fibers play in the removal of the particulate. Smaller fibers, less than 5 microns, contribute to removal of submicron particulate, and they generally restrict the fluid drain rate. 5 to 15 micron fibers remove large particulate and facilitate fluid draining.
Well, speaking of the importance of fiber selection and the technology evolving in time, I'm very excited about a new high-temperature ceramic filter which works up to 2,500 degrees Fahrenheit. And although these filters are not used for aerosol, they do present new opportunities for high-temperature filtrations of solids. The report tested various bed depths, with some up to a foot thick.
It may seem odd to us now, but remember they had sand filters several feet thick that they were replacing, so 12 inches was reasonable for their research.
Now, once again, the bed depth falls largely into the system provider's design criteria, but it is important to understand the impact that bed depth has on the design.
Yes, but we have a few special designs, each unique to a customer's process. As a rule, increasing bed depth generally improves efficiency with little increase in pressure drop across the filter.
Bed depth and bed density generally work together with respect to the efficiency and pressure drop.
Yes, they do. You can increase the density. Increasing density generally improves efficiency with an increased pressure drop. Surface area is really where decision makers have a choice in the design process.
The Hanford report demonstrated that fiber bed mist eliminators have a substantial operating range.
Yes, that is, they function in terms of collection efficiency between 10 and 40 feet per minute.
Increased surface area equals slower bed velocity, improved draining of liquids, thus a lower pressure drop. Increased surface area also means that there is more dirty side surface with more holding capacity for solid particulates if they are present. Generally, it is a safer design that is adaptable to more processes.
Slower bed velocity is also the most costly option.
But is it? Certainly it is more costly capital cost-wise, but how about total cost?
There are a couple of ways to support the filters. With hanging filters, you have a larger surface on the inlet side, which equals a longer life.
Please note the liquid recovery section on the left illustration. When the mist is coalesced into liquid droplets, the drops drain down into the sump and eventually have to be removed. The filters can sit on the tube sheet, and this method drains well, but in general it has a shorter life because there is less filter area on the inside diameter versus the outside diameter. There is also less potential, however, for droplet entrainment due to the decreasing velocity as the air moves from the smaller inside diameter to the larger outside diameter.
So how does the selection committee use the design criteria to make a selection on competing systems?
That's really the question. Let's take a look at a very real case study where we associate costs for 3 systems with different velocities and compare them side by side.
We have provided a number of similar projects to this, so the data is representative and should be very useful. It's for an asphalt coating saturator and coater. It's 10,000 ACFM at 100 to 120 degrees Fahrenheit, moderate aerosol loading, roughly 5 pounds per hour, operating 4,000 hours a year, with electric cost at 12 cents a kilowatt hour, and 3 flow velocities across the face of the filter, 15, 30, and 40 feet per minute.
The curves in the Hanford report that correlate velocity with pressure drop were also helpful here in defining what the pressure drops and subsequent energy costs will be at the different velocities. All right, this slide is really got a lot of information on it. Let's start with the pressure drop column. We have pressure drops that ranges at the top from 2 inches water column to 22 inches at the bottom. The next column associates the horsepower that will correlate with the given pressure drop. For example, if we look at the first line, 2 horsepower would correlate to 11.5 brake horsepower. Moving over to the third column, we've converted that into kilowatts. The next column applies the 12 cents per kilowatt, and we get dollars per hour. Multiplying by the 4,000 hours a year of operation, and finally we end up in the final column with electric cost per year. So as you see in the first line, we have $4,117.92 if the filter system were to operate at 2 inches of pressure drop for the entire 4,000 hours. And these pressure drops are average pressure drops as we apply them down in the next few slides. The 22-inch extreme on the bottom equates to $19,264.70. So you can see the effect pretty dramatically that pressure drop has on the operating cost. This chart is what we're going to use to fill in, and it takes the pressure drop and the dollars per year over a 6-year period. And in column 2 there, you'll see that the pressure drops go up from 2, 4, 6, 10, 12, and then in year 6, it drops back down to 2. In the other areas under the 30 feet per minute, the pressure drop is 10, 16, 8, 16, 8, and 16. And the reason for these different pressure drops has to do with the time periods or the life of the filters when the filters reach capacity and have to be changed out.
We're jumping back to the previous slide for a second just so that you can see where the operating cost comes from for the different pressure drops. You'll see the delta P on the left, and on the right side you'll see the electric cost per year.
So now we have the slide filled in with the corresponding dollars per year for the various pressure drops. So if we look at year 1, for each case, we start off with an average of under the 15 feet per minute for average pressure drop of 2 inches water column, and the electric cost is $4,118 per year. In the 30 feet per minute, the filter pressure drop averages 8 inches and $8,415 per year, and the 40 feet per minute, 18 inches at $16,078 per year. So you can see that we're already seeing the effect of having a higher velocity, higher pressure drop system is costing more per year for the electric use.
And the difference in these electrical costs is substantial when we add it up over the life of the equipment. Another major contributor to the overall cost of the unit is the filter replacement cost. With the 15 feet per minute, there are more filters, so the filters last longer. There's 40 filter elements, and the replacement cost at the end of their 5-year life is $30,000. With the 30 feet per minute, there's only 20 filters, but there's less filters, but you have to replace them every second year, and that's $22,000 every time you replace them. With the 40 feet per minute face velocity, there's only 15 filters. You have to replace them every year, at a cost of $19,000 for the filters.
The pressure drop and the replacement filter cost are interrelated because the fan horsepower is finite, and once it reaches the filter's capacity, the filters needed to be replaced to allow for the flows that we need. In other words, as the filters restrict and the horsepower is at capacity, we can no longer get the flow, so we have to change the filters. Also, velocity means that the draining is slower. Increased velocity means that the draining is slower, which also affects the delta P.
Yeah, the filter life at the 15 feet per minute face velocity for 40 filters is 5 years versus 1 year for the 40 foot per minute face velocity.
And when you think about it, a 15 feet per minute has to do the same amount of work as a 40 feet per minute with less filters and less surface area.
This chart illustrates the total cost of the unit, the initial capital cost, the operating cost for electricity, the operating cost for replacing filters, so your total O&M, your total cost of ownership. And after a 6-year time period, your 15 feet per minute filters, total cost of ownership is $188,000. The 30 feet per minute, your total cost of ownership is $224,000. With the 40 feet per minute, your total cost of ownership is $259,000.
That's based on 6 years, and really, that 6-year period could really be extended out somewhat.
It's true. We have some units out there that are approaching 40 years of operation.
I would say that 20 years is a very reasonable average life for these types of systems.
It's obvious if you have the capital, it's a good long-term investment to go with the slower velocity design. The case study we just looked at reviewed deals with some real applications. However, it's a very straightforward case.
The process temperature was an ideal 110 to 120 degrees. But we know that there are other factors that sometimes influence system cost as well.
Yes, as mentioned, temperature is one big factor. However, in some cases, solid particulate is a big issue.
Rich, perhaps you can explain how the process temperature impacts the design of a filter fiberbed mist eliminator.
Sure. Remember that a fiberbed mist eliminator is a device used to remove liquid aerosol from processes. An aerosol is a liquid droplet. Therefore, if the temperature is too hot, the organic material, oil, etc., is in a vapor form and will pass through the filter as a vapor bed without coalescing and therefore not be removed.
The question is precisely what temperature do we need to be at to achieve the desired results? And the answer varies based on the materials to be removed. But in general, a process temperature of around 120 degrees will give us about 99% removal efficiency of 0.1 microns.
So remember, cooler is better.
There are a few different approaches used to lower the process temperature when it is above the desired operating temperature, but generally we focus on 4 methods.
I'll briefly try to explain the 4 methods. You can add dilution air to the hot process air, and the 2 streams together will come down to the desired 120 degrees temperature. The next option that we use occasionally is an air-to-air heat exchanger, where we'll cool the process air with ambient air in a tubular heat exchanger. The third option is to use a fin-coiled or a non-fin-coiled cooling coil, where you'll run water or another cooling medium through the coils, and the air passes over the outside of the tubes and gets cooled by the water on the inside. And then the fourth method we use would be adiabatic cooling, where we spray water into the air and the evaporative cooling will reduce the overall process temperature.
Dilution air is generally used when the process flow is smaller or when the temperature is close to that of the desired design temperature.
The downside of dilution air is it increases the size of the filter unit because the dilution air and the process air move together through the system and must be run through the filters at the design face velocity. What you're looking at here is an ambient air inlet valve on the inlet to a unit, and it's temperature controlled to vary the amount of ambient air needed to maintain the correct temperature going through the filters. The next option is to use an air-to-air heat exchanger, where we will blow ambient air over the outside of the tubes and have the process run through the inside of the tubes. And it will reduce the temperature of the process down to the 120-degree desired temperature.
This is a great approach when there's a use for clean recovered heat somewhere in the nearby building.
In this slide, you're looking at a pictorial of a system with an air-to-air heat exchanger. On the bottom left, you have an ambient air fan, which blows air over the tubes, and the process comes in and flows down through the tubes so the tubes can drain and be easily cleaned if any particulate collects in them. And you'll blow a much higher quantity of air, SCFM of air, over the outside of the tubes so that you can get the process down to the 120. So there'll be a larger volume of air going as cooling air, and the process will be the smaller volume.
Of course, when we do this, we're adding a lot of equipment. We've got a heat exchanger, we've got another fan, and also the controls to maintain the temperature balance that we're looking for. So unless there's a need for that clean 240-degree recovered air, this generally is not a good way to go because of the additional cost. By indirect, we mean that the air and the water do not come in direct contact.
Yeah, this is similar to the air-to-air, except in this case, the cooling medium is achieved by putting water on the other side of the heat exchanger.
This is a good approach when the airstream is free of solid particulate, but it can be a maintenance problem otherwise. Also, to be cost-effective, it's good to have a need for the heated water.
In this pictorial, you see the dirty process comes in on the left side of the slide. It goes over the outside of the tubes of the cooling coils, and the water's on the inside of the tubes. And as the water in the cooling coils absorbs the heat from the process, reducing the temperature down to 120 degrees. Then it flows out of the cooling coils and goes through the coalescing filters. And then after going through the filters, goes over towards the process fan inlet.
Adiabatic cooling, or evaporative cooling, is when there is a direct contact with the water and the hot air. This is a very effective means to lower hot process temperatures.
In some textile ovens, the exhaust air temperature can be as high as 350 degrees Fahrenheit.
Even higher, in some heat set ovens, the temperature can be as high as 400 degrees.
The secondary benefit of this method is you get additional scrubbing of the process.
Yes, that's true, especially when the particles are large inorganics such as stone dust or fibers.
On this pictorial, you see the dirty process air coming in on the left side of the slide. It flows in the bottom of the unit, goes up through a cyclonic scrubber where water is sprayed from the sump down in a counterflow fashion through the air, like a counterflow scrubber. After it goes through the cyclonic scrubber, it goes up through a mist eliminator to remove the larger droplets. After going through the mist eliminator, it flows down under a baffle and flows through the outside of the filters. After passing through the filters, it goes to the inlet of the process fan.
When cooling is required, I would say that this is probably the most frequently used cooling process because it is cost effective and is very efficient at cooling.
The picture that you're looking at here is a cyclone scrubber. This is the heart of our cyclonic scrubber. The water is sprayed down in the downflow, and the air flows up through the cyclone.
The cyclone section is stationary, but it imparts a turbulent motion to the airstream while the water is being sprayed counterflow to the air direction.
What you're looking at here is a picture of the spray nozzles spraying the water down onto the cyclonic scrubber. We have removed one of the mist eliminators so we can get a view of the spray nozzle. Another potential parameter for cost impact is the control of any solid particulate. If it's present, the particulate can blind the filters and drastically reduce the life of the filter elements.
Yeah, as we stated before, as years went on, we've applied these fiber beds to different applications. And some of the applications that these filters were put on had problems with solids in the exhaust. But fortunately, the problem has been efficiently addressed with two methods of pre-filtering these solids from the airstream. The first approach, and the simplest, is the use of a pocket pre-filter to remove the solids.
These filters are a low-cost solution, but they do require the process to be off to change out the filters. What you're looking at in this side is a typical pocket pre-filter. It has a metallic frame on the right, which is the inlet side, and the flow, they are generally oriented with the pockets down, and the flow would be down through the pocket pre-filter, and the pockets add a lot of extra square feet. So in one 2-foot by 2-foot area, you get a lot of filtration square feet. So you get a long-lasting filter.
Each individual filter panel can handle about 2,500 CFM of air.
With the larger flows, we group multiple pre-filters together. The largest grouping I recall is 20 pre-filters.
At that point of 20 filters, the space needed becomes substantial. The indexing pre-filter solves the footprint problem with the use of a drum. This method provides a large surface area in a fairly small space.
While the indexing pre-filter is a more costly approach, it provides for weeks of uninterrupted operation. In this slide, you're looking at an indexing pre-filter that's a standalone. The inlet would be on the top. The flow is through the drum and then comes out the end of the drum as pre-filtered air with the solid particulate removed. There's a roll of clean media, which is on the top, and then there's a roll of dirty media. As the media gets dirty and the pressure drop starts to go up, we have a pressure differential switch, which will initiate a timer to turn the drum and roll on clean media. So the pressure drop goes down again until the media gets dirty and needs to be indexed again.
Yes, this is a standalone indexing device, which I believe was used to protect the heat recovery media on an RTO. Normally, this same indexing drum that you just described is integrated into the filter system.
This slide shows a fully integrated system that you just mentioned.
Yeah, the inlet shown at number 1 is followed by the cooling section with the cyclonic scrubber and the water sprays, which is then followed by the indexing filter, pre-filter, and finally by the Fiberbed Mist Eliminator filters.
The addition of the cooling section on a Fiberbed Mist Eliminator is necessary when the process temperature is too hot for effective filtration, but the pre-filter isn't essential.
That's true. The decision whether or not to include a pre-filter is based on the extending the filter life of the main elements, not about performance of the system.
Additionally, in the case of the indexing pre-filter, the dirty media changes frequently to keep pressure drop low, so you're saving on electricity as well.
Let's take a look at the cost impact associated with both the pre-filter and cooling options.
The second column shows the cost of the 10,000 CFM system we detailed earlier. So the first item in column 2 is $115,000, which is the base price of the unit with the 40 coalescing filters.
The next item in column 2 is a unit using dilution air to do the cooling. And then it's followed by an air-to-air cooling coils, air-to-air / cooling coils is next, and finally direct water cooling.
On a pure cost basis, the cooling coils and adiabatic cooling are the best options for cooling.
There are 2 columns to the right, one for each type of pre-filters. The prices under the pre-filter columns include the cost for the corresponding cooling options.
So in the last column, under indexing, a unit with no cooling and an indexing filter costs $130,000, compared to an indexing filter with an adiabatic cooling costs $137,000.
Yes, that's correct. In every case, the pocket pre-filter is a lower cost option.
The long period of uninterrupted operation can quickly justify the cost difference of the indexing pre-filter. There are a lot of parameters that should be considered when designing or selecting a fiberbed mist eliminator.
Of all the very important parameters we've touched on in our discussion, which ones do you feel are the most important, that have the critical impact on a particular project?
It's hard to say. Certainly, number 4, surface area versus velocity, impacts the price as we detailed earlier, but temperature must be addressed when it is above the 120-degree threshold.
Yeah, I would agree with number 4, but not far behind is a solid issue. I've seen similar projects have vastly improved filter life, and therefore cost to own significantly improved by addressing the particulate issue with a pre-filter.
What this comes down to is collecting as much process information as possible and applying them to design.
Definitely, a case-by-case evaluation is essential. Asking the right questions and having enough knowledge so that you understand the answers that you are given will help you quantify your selection and greatly improve your chances of a successful project.
Well, that concludes our presentation for today, and we would be interested in answering any questions. We do appreciate you attending our webinar, and at this point, we'd like to answer any questions that anyone has for us.
The first question, how frequently do you have to change the filters? The average ranges between 3 to 5 years. Some, however, have to change every year if there's a large particulate or some other condition. But 3 to 5 years is a good average for the expectancy of the life of the main filters.
We have a question here from one of our attendees about what does FPM mean, and that would be feet per minute, which is a key design criteria for the velocity of the air going through the inlet side of the filters. The point is that the lower that number is, the more filters you need, but the lower that number is, the longer the filters last. So it's a key design parameter for our system.
Next question. How many filters are there in a typical system? That number varies, as we discussed earlier, based on a couple parameters, the CFM, the cubic feet per minute, as well as the design velocity that is selected. We have units with one filter in for tank vents, and I think the most we've ever put in one particular assembly is about 160.
We have a new question that came in. Are the filters good for persistent organic pollutants, dioxin, furans, SOx, CO, and NOx? These are coalescing filters which coalesce liquid droplets, submicron liquid droplets that you would see at many facilities as a blue haze smoke coming out of a stack. If they are a vapor, or a gas like carbon monoxide or NOx, these filters will not remove NOx or carbon monoxide. So there are filters for coalescing submicron oil droplets, which are the blue haze that you see coming off of heated oil tanks or off of processes such as textiles, where they heat a textile with has dye on it, and the oil and the dyes come off as blue smoke.
There's a question, what is the advantage of using a mist collector
in front of a RTO. RTO meaning regenerative thermal oxidizer. Yeah, we touched on that earlier. The use of the fiber bed in some situations helps remove the coalescing portion. Some processes have a combination of emissions that are removed by the fiber bed filters, and such as an oil, mist, as well as other VOCs, volatile organic compounds, which are not removed in the fiber bed. So as an example of that, a asphalt saturator or other process in the asphalt shingle business may contain both asphalt mist, which is removable by the fiber beds, and volatile organics such as maybe a toluene or xylene, something like that, that is not. So by removing the condensable portion of it, it greatly reduces the buildup of this condensables on the cold side of the recovery beds, and makes allows the RTO to oxidize those volatile organic compounds and not be burdened with the condensable portion of it. Is the Blue Haze in compliance with the EU legislation or the EPA? I believe what we're asking there is the Blue Haze, once it passes through the fiber bed filters, going to be compliant? And yes, even with the more restricting requirements, we are virtually zero opacity as they come through. 99% of 0.01 microns and larger are removed in this process when the temperature is controlled, as discussed, to the 120 Fahrenheit range.
On the case history, there's another question come in. Is there any case histories in fluorides? If the fluorides are in a liquid droplet form, the fiber bed mist eliminators will remove the liquid droplets. However, because fluorides can be rather corrosive, the materials of construction have to be evaluated closely with the customer to make sure that we provide a system with long life. We have made filter systems from carbon steel, from stainless steel, we've made systems from Hastelloy, AL6XN, so we have to do an evaluation with the customer to make sure that the materials of construction are correct so they get a long life. But yes, the fiber bed mist eliminators are very common in acid systems, and they've been used for a long time in sulfuric acid also. But you just have to make sure you get the right materials of construction so we don't have corrosion issues.
Next question, another question here. Are there mist eliminators available operating at temperatures greater than 500 degrees Fahrenheit? I personally don't know any that are greater than 500 degrees Fahrenheit, but what would happen in that case is that with the adiabatic cooling, which is very effective, it only works up to a certain point until the airstream becomes saturated. We would have to look at it on an individual case basis, but it would probably require 2 stages of cooling to get the adequate cooling we need. But that would definitely be a unique, one-of-a-kind look at the application and come up with something very specific to that case.
All right, there's a good question here. Are our units mobile? We have designed units that are built on a flatbed truck or a drop deck trailer, and they're used in the asphalt industry, where they move a macadam plant from one location to another. So yes, our units can be mobile. They can be built in with a built-in set of wheels, or they can be picked up and stored on a truck. Our pilot units are very small and are easy to move from one site to another.
Rich just mentioned a pilot unit. Another question here regarding the pilot units. We do have pilot units that can be placed on a site. They can be configured in different ways to show one or more different means of cooling, as well as the two primary pre-filter options. These are generally about 500 to 1,000 CFM in size.
Here's a good question from a customer. What are the sampling steps required to determine if pre-filtering is required for a system? Basically, it's very important for the customer to understand and for us to understand what is the incoming process stream and what is the loading of solid particulate. So there's EPA has a very standard test for testing for solid particulate. And we do recommend that if you're not sure, that you have that test done ahead of time so that we can know the particulate size, what the particulate is made of, and the particle size distribution. So there's a standard EPA test for solid particulate.
A question about export. Do you export, and are you pricing competitive against specific RIM air pollution control equipment or the European equipment? Well, the competitive side of it, that's again on a individual case basis, but we believe we are. As far as the Pacific Rim, we largely do. We've done units in both China and South Korea. We have a partner in China, and we also have associates in South Korea. So a large portion of our manufacturing of the vessels themselves are done locally, and we supply the filters as well as the controls in most cases from the United States. So yes, that makes us, I believe, competitive in the those overseas markets. We haven't done much, frankly, in the European arena, however. Will this technology be effective for controlling oily condensables particulate matter that may be released from rubber curing processes or in the textile industry? Absolutely. Addressing the textile industry first, probably 20 to 30% of the active units that we have currently operating are in the textile end of it, both in the center frame where we're doing heat set, as well as coaters, that type of thing. Rubber curing process is also a very good application for the Fiberbed Mist Eliminators. There are numerous applications where rubber coating of fibers is also a good application.
And then I have a question here about the table on our statement of work. The CFM was designed for 10,000 cubic feet per minute, which is fairly typical for that one type of customer we have, which is in the asphalt business and the shingle making business. So it's a typical shingle plant. So that's where that 10,000 CFM came from. We've made a fair amount of those pieces of equipment.
Okay, I think that's about all the time we have right now. We will address the additional questions that we have received very shortly here in the next day or so. I'd like to thank you all for joining us today. Again, thank you very much, and we will respond to any questions that haven't been answered very shortly.
Thanks again for attending.